In the mid-1960s, Soviet air defense forces quietly accepted a new interceptor into frontline service with a combat radius so severely restrictive that fulfilling its primary mission essentially guaranteed the loss of the aircraft. If an American strategic bomber came over the Arctic Circle and the interceptor was scrambled from a northern base, Soviet doctrine mathematically accepted that the pilot would run out of fuel during the return leg. After expending his missiles at Mach 2, the pilot was expected to point his jet back toward friendly territory, glide until the turbine starved, eject over the frozen tundra, and hope a search and rescue helicopter found him before the exposure did. The aircraft was the Sukhoi Su-15, known to NATO as the Flagon, and it was not a fighter jet in any traditional sense. Structurally and doctrinally, it was designed as a reusable first stage for the massive air-to-air missiles it carried under its wings. To understand how an aviation powerhouse like the Sukhoi Design Bureau arrived at such an extreme compromise, you have to look at the terrifying strategic arithmetic of the early Cold War. The Soviet Union covered an immense landmass, a sprawling expanse of 11 time zones that was completely impossible to defend with a continuous wall of surface-to-air missile batteries. The threat keeping Soviet generals awake at night was not the nimble dogfighters of the US Navy or Air Force, but rather high-altitude, high-speed nuclear bombers, specifically the B-58 Hustler and the looming specter of the Mach 3 XB-70 Valkyrie. The Soviet PVO, Vojska Protivovozdushnoye Obrony, or National Air Defense Forces, needed a machine that could sit on alert status, scramble in minutes, climb like a rocket to 60,000 feet, and lob heavy ordnance at a supersonic bomber before it reached its release point. Dogfighting was irrelevant. Loiter time was a luxury. Everything was sacrificed on the altar of climb rate, top speed, and radar aperture. If you enjoy detailed deep dives into military engineering, aviation strategy, and the history behind these complex machines, subscribe to the channel. I've got a lot more planned. The Su-15 was born out of the absolute failure of its predecessors to meet these uncompromising demands. In the late 1950s, the Soviets relied on the Su-9 and Su-11, which were essentially flying engine tubes with a shock cone in the nose intake housing a tiny radar. But physics dictates that a radar's detection range is heavily dependent on the physical size of its antenna. A small nose intake shock cone simply could not house a radar dish large enough to detect a fast-moving bomber in time for the pilot to maneuver and fire. Sukhoi engineers knew they had to abandon the nose intake entirely and install a massive, unobstructed radome on the front of the aircraft. This single requirement, a giant nose to hold a giant radar, triggered a cascading series of aerodynamic and engineering challenges that defined the Su-15's entire existence. By moving the radome to the nose, the engine air intakes had to be shifted to the sides of the fuselage. Side intakes on a supersonic jet are notoriously difficult to design because they must cleanly separate the turbulent boundary layer air tumbling along the fuselage from the smooth air entering the engines. If turbulent, slow-moving air enters a jet engine at Mach 2, the compressor stalls, the engine flames out, and the aircraft turns into a very heavy, very unaerodynamic glider. Sukhoi's solution was to design large rectangular side intakes with variable geometry ramps, separated from the fuselage by a distinct splitter plate. This ensured only clean, supersonic air reached the shock ramps, where it was slowed to subsonic speeds before hitting the compressor faces. But pushing air through a longer curved duct meant drag and pressure losses. A single engine was no longer going to provide the raw thrust required to push this newly bulked-up airframe to Mach 2.2. The design transitioned into a twin-engine layout, utilizing two Tumansky R-11F2S 300 turbojets, later upgraded to the R-13-300 series. These engines were marvels of brute force engineering, capable of generating over 14,000 pounds of thrust, each in full afterburner. They were purely optimized for high-altitude, high-speed flight. However, this raw power came with a hidden cost that defined the Su-15's operational reality. Turbojets of this era possessed an utterly insatiable thrust-specific fuel consumption rate. When a Flagon pilot pushed the throttles past the detent and ignited the afterburners, the twin Tumanskys drank fuel at a rate that drained the internal tanks in a matter of minutes. The airframe simply could not carry enough kerosene to offset the appetite of its propulsion system. The Flagon had a maximum internal fuel capacity of around 6,800 liters. In a full afterburning zoom climb to intercept altitude, a massive percentage of that fuel was gone before the pilot even leveled off. This extreme thirst forced Sukhoi to make further aerodynamic compromises. To maximize internal volume for fuel, the wings had to be exceptionally thin, which mandated a pure delta wing planform. A delta wing is brilliant for supersonic flight. Its high sweep angle delays the onset of wave drag, and its structural rigidity allows it to withstand immense aerodynamic loads at high speeds. But a pure delta wing produces relatively little lift at low speeds. To keep a delta-winged interceptor airborne at approach speeds, the pilot has to fly at a terrifyingly high angle of attack, pointing the nose at the sky and dragging the aircraft onto the runway using engine thrust to arrest the sink rate. For the early Su-15s, the approach speed was a blistering 320 kilometers per hour, roughly 200 miles per hour. Landing a Flagon in a crosswind on a snow-covered Siberian runway required an extraordinary level of skill and nerves of steel. The aircraft landed so fast, and the brakes were under such immense thermal stress, that a drag chute was absolutely mandatory on every single landing. If the chute failed to deploy, the aircraft was highly likely to run off the end of the concrete. This precarious low-speed handling created an exhausting environment for the pilots, shifting the perspective from the drawing board to the bleak reality of the cockpit. Once strapped into the Su-15, a pilot was not given the freedom of a hunter looking for prey. They were treated as a biological component of a massive ground-based air defense network. The heart of this network was the Vozduk-1 Ground-Controlled Interception (GCI) system, and its airborne component inside the Su-15 was known as the Lazur data link. Soviet interceptor doctrine was fundamentally different from the West's approach. In the West, pilots were given a general vector, expected to acquire the target on their own radar, and autonomously manage the intercept geometry. The Soviets trusted their ground controllers far more than their pilots. When a Flagon scrambled, the pilot did not immediately turn on his radar. Instead, he relied on the Lazur system, which received continuous telemetry from massive ground-based radar stations. The ground controller calculated the exact trajectory of the target and beamed steering commands directly to the pilot's flight instruments. The pilot simply kept a set of command needles centered on his artificial horizon. The ground network controlled the interceptor's heading, altitude, and even commanded when to engage the afterburners. The pilot was essentially a meat servo, executing a mechanical task. This heavy reliance on ground control was a direct consequence of the radar housed inside that massive nose cone. The original Oriole D Eagle radar was powerful, capable of burning through electronic countermeasures, but it was technologically primitive. It was a simple pulse radar, meaning it could not look down and distinguish a low-flying aircraft from the radar clutter reflecting off the ground. If an American bomber dropped to low altitude, the Su-15's radar became useless, completely blinded by the Earth's surface. Furthermore, the radar's field of view was narrow, and its processing speed was slow. The pilot only switched the radar on during the final moments of the intercept, right before weapons release, strictly to provide a target lock for the missiles. So, after seeing how tightly controlled and mathematically rigid this operational approach was, do you think this design philosophy was actually an effective way to defend a massive airspace, or was it a fatal over-reliance on centralized command? Let me know your thoughts in the comments. The rigid nature of this system meant that when things went according to plan, the Su-15 was a terrifyingly efficient interceptor. A B-52 cruising at 40,000 feet would be detected by ground radars, a Flagon would scramble, fly a mathematically perfect curve calculated by a ground computer, and arrive in the bomber's blind spot. But combat rarely goes according to plan, and the Su-15's design left the pilot completely unequipped to deal with the unexpected. The armament of the Su-15 reflected its uncompromising design. Early variants completely lacked an internal gun. The prevailing theory of the 1960s was that supersonic combat would be settled entirely by missiles, and a cannon was considered dead weight. The Flagon's primary teeth were the R-98 missiles, known to NATO as the AA-3 ANAB. These were massive, heavy weapons designed to ensure a catastrophic kill against a large bomber. A standard Su-15 loadout consisted of just two R-98 missiles under the wings. one radar-guided and one infrared-guided. This mixed loadout was a clever Soviet solution to the unreliability of early missile technology and the increasing threat of Western electronic warfare. If an American bomber successfully jammed the radar-guided missile, the infrared missile, tracking the intense heat of the bomber's engines, would still find its mark. The pilot was trained to fire both missiles in a staggered salvo at the same target to guarantee a kill. However, carrying only 2 missiles meant the pilot had exactly 1 pass to get it right. There was no capability for a sustained engagement. If the pilot missed, or if the missiles were spoofed by flares and chaff, the Su-15 did not have the fuel to circle back for a second run, nor did it have a gun to close in and finish the job. It was a one-shot weapon. Engineers recognized the vulnerability of a missile-only platform after observing air combat over Vietnam, where American Phantoms frequently found themselves engaged in turning fights without a gun. Sukhoi hastily developed twin-barrel 23mm gun pods, the UPK 23-250, that could be bolted to the belly pylons of the Su-15. While this gave the aircraft a desperately needed close-range weapon, the pods added immense aerodynamic drag, further crippling the aircraft's already marginal range and punishing its fuel economy. As the years passed, the Su-15 underwent continuous modernization to address its glaring flaws. The most significant visual change occurred with the introduction of the Su-15TM variant, which featured a cranked delta wing. Engineers altered the leading edge of the wing, introducing a distinct kink that increased the wing area and provided a slight boost to aerodynamic lift at lower speeds. This compound sweep modification finally brought the terrifying approach speeds down from 320 km per hour to a slightly more manageable 300 km per hour, easing the burden on the pilots and reducing the strain on the landing gear. The avionics were also overhauled. The primitive Oriole radar was replaced by the much more capable Typhoon radar system. While still lacking a true look-down, shoot-down capability, the Typhoon was significantly more resistant to jamming and offered better target tracking. Despite these upgrades, the fundamental nature of the aircraft never changed. It remained an uncompromising, fuel-hungry, high-speed platform tied intimately to its ground controllers. To truly understand the operational reality of the Flagon, it is helpful to contrast it with its closest Western counterpart, the Convair F-106 Delta Dart. Both aircraft were born in the same era, utilizing pure delta wings and built for the exact same mission, intercepting high-altitude bombers. But their underlying philosophies were entirely different. The F-106 relied on the incredibly complex MA-1 fire control system, an early analog computer that essentially flew the aircraft during the intercept. However, the F-106 pilot retained significant autonomy and situational awareness. More importantly, Convair designed the F-106 with a massive internal weapons bay. All of its missiles, and later an M61 Vulcan rotary cannon, were housed inside the fuselage. This left the F-106 aerodynamically clean, allowing it to easily cruise at supersonic speeds without the massive drag penalty of external stores. The Su-15, in contrast, hung all of its weapons, drop tanks, and gun pods outside the airframe in the slipstream. While a clean Su-15 could theoretically reach Mach 2.2, a fully loaded Flagon with missiles and drop tanks struggled to push past Mach 1.5, and its acceleration dropped dramatically. The F-106 was an elegant integrated weapon system. The Su-15 was a brute-force sled meant to haul ordnance to an altitude and point it in a general direction. This extreme optimization for a nuclear bomber war that never happened meant that the Su-15 was uniquely unsuited for the messy, ambiguous reality of peacetime airspace policing. When tasked with intercepting unidentified targets that weren't flying straight and level at Mach 2, the Flagon's design flaws cascaded into operational disasters. This tragic mismatch between design and reality was brutally exposed not once, but twice on the global stage. In April 1978, Korean Airlines Flight 902, a civilian Boeing 707, strayed off course due to navigational errors and inadvertently violated Soviet airspace near Murmansk. The PVO scrambled a Su-15 to intercept. The Soviet pilot found the airliner, But the rigid Soviet command structure and the interceptor's design limitations created a chaotic situation. The Su-15 pilot reportedly identified the aircraft as a civilian airliner, noting the Korean Airlines logo, but his ground controllers, looking only at blips on a radar screen, ordered him to fire. The pilot fired an R-98 missile, which detonated near the airliner's wing. Miraculously, the damaged 707 managed an emergency landing on a frozen lake, though 2 passengers were lost in the depressurization. The flaws exposed in 1978 were entirely ignored, setting the stage for an even more devastating failure 5 years later. On September 1, 1983, Korean Airlines Flight 007, a Boeing 747 carrying 269 people, drifted heavily off course and crossed the Kamchatka Peninsula and Sakhalin Island. The Soviet air defense network, already on high alert due to recent American reconnaissance flights in the area, tracked the intruder. A Su-15TM, piloted by Major Gennady Osipovich, was scrambled to intercept. The events that followed over the night skies of Sakhalin perfectly encapsulate the fatal inflexibility of the Su-15. Osipovich was vectored perfectly by his ground controllers, coming up behind the unidentified aircraft. However, a Boeing 747 cruising at altitude flies much slower than the minimum comfortable speed of a Su-15. To avoid overshooting the target, Osipovich had to constantly work the throttles, deploy his air brakes, and ultimately lower his landing gear and flaps just to induce enough drag to stay behind the airliner. He was vibrating on the absolute edge of a stall, fighting a delta wing that desperately wanted to drop out of the sky at low speeds. In this high-stress environment, Osipovich attempted to fire warning shots using his UPK-23 gun pods. But Soviet logistics dictated that armor-piercing shells rather than highly visible tracer rounds were loaded into the interceptors. In the pitch blackness of the night sky, without tracers, the crew of the 747 had no visual indication they were being fired upon. Because the Su-15 lacked advanced optical sensors, and because it was too aerodynamically compromised to safely pull alongside a slow-moving target in the dark to establish visual contact, Osipovich was forced to rely entirely on ground instructions. The GCI commanders, unaware or unconcerned with the visual reality, treated the radar contact as a hostile military target. With time and fuel rapidly running out, the eternal curse of the Flagon, Osipovich was ordered to destroy the target. He fired 2 R-98 missiles, neutralizing the aircraft and resulting in the tragic loss of all 269 souls on board. The KAL-007 incident shocked the world, but from an engineering and doctrinal standpoint, the Su-15 performed exactly as it was designed to. It scrambled quickly, climbed to altitude, intercepted the target via ground control, and successfully deployed its weapons. The failure was not a malfunction of the machine, but a malfunction of the philosophy that created it. By designing an aircraft so highly specialized for a singular apocalyptic scenario, destroying a fast-moving bomber in a Third World War, the Soviets had built a machine completely incapable of nuance, identification, or flexibility. The Su-15 was a product of paranoia, an airframe wrapped around a massive radar and twin turbojets, built to operate in an environment of absolute certainty. When introduced to ambiguity, the machine's limitations, its terrible low-speed handling, its fuel poverty, its lack of pilot autonomy, forced operators into split-second catastrophic decisions. Following the international outrage of KAL-007, the Su-15 continued to serve, but the writing was on the wall for the dedicated single-purpose interceptor. The Soviet Union realized that airspace defense required aircraft that could do more than just fly fast in a straight line. The introduction of the fourth-generation Su-27 flanker and the MiG-31 Foxhound rendered the Flagon obsolete. The Su-27 offered immense range, incredible maneuverability, and true look-down, shoot-down radar capabilities. The MiG-31 took the high-speed interceptor concept and modernized it, introducing a phased-array radar, a dedicated weapons system officer, and the fuel capacity to loiter on patrol for hours. By the early 1990s, with the collapse of the Soviet Union, the massive fleet of Su-15s was rapidly retired. The new Russian Federation could not afford to maintain a fleet of single-role interceptors that guzzled fuel and offered no multi-role capability. The aircraft were flown to aircraft boneyards, their wings clipped to comply with arms reduction treaties and left to corrode in the very Siberian snow they were built to defend. Today, the Su-15 is largely remembered for the tragedies it was involved in, rather than its engineering achievements. Yet, ignoring its mechanical legacy is a mistake for any serious student of aviation. The Flagon represents the absolute zenith of 1960s interceptor design, a physical manifestation of Cold War anxiety. It was an aircraft where every comfort, every safety margin, and every ounce of flexibility was stripped away in the singular pursuit of intercept geometry. It was a one-way machine, piloted by men who were fully prepared to trade their lives for a chance to stop a nuclear payload. Ultimately, the Su-15 was highly successful at the mission it was designed for, but tragically disastrous in the missions it was actually assigned. It serves as a stark historical reminder that when engineers optimize a weapon system to an extreme degree, they often strip away the human pilot's ability to correct course when the fog of war descends. If you like this deep dive into the engineering and history of Cold War aviation, leaving a like helps get it out to other military history fans. Thanks for being here.